Hello and welcome to our final session of the DAX Studio tutorials. Today we're going to be talking to Marco Russo about his contributions and all of his knowledge around the performance tuning inside DAX Studio. All right, we are at the top of the hour. Let me get myself off the screen here. We'll get Marco going. And so let me transition here real quick. All right. Marco, you are live. We have my sharing screen, so feel free to switch your screen share. Feel free to take over the screen share if you need to, and okay. We'll get going. Okay. Again, thank you very much for your time today. This is awesome. I'm really excited to learn more today. This is going to be amazing.
Thank you very much. Thank you very much, Mike. I'm going to share my screen, and so the session today is about query performance with DAX Studio. And the idea is that I start from Power BI now, and in a minute I will show you DAX Studio, and I will show you how to use a few features of DAX Studio to understand what is the performance of a specific query, but also how we can use other metrics provided by Power BI and the performance analyzer of Power BI in particular. So, sorry, this is the wrong file. Let me get this one. Okay, yep. So this is the file where I want to start.
And one more question here real quick. Would you mind just minimizing my little video in the bottom right?
Oh, yes,
corner?
You're right.
Yeah, we'll get a little more landscape for your
You're right. I
your screen share. Yeah, no problem. No worries.
Okay.
We'll just, good to go.
Good. So let me just move another window around here. So I have this one here. Okay, good. So I have a couple of Power BI files that I will use just to have something to analyze. And the first file I use now is a very simple model that has a page with a number of visuals that generate a number of queries. So you see that there are two pages here. One is sales. And please pay attention. When I will click sales, you will see for the first time in this page the visualization of several visuals. You will notice that some visual requires just between 0 and 1 second, and another visual a few seconds. The one on the bottom left of the page. So here we go. I start this, and you see that this requires time. And where is the time spent? It's time spent in the visual. It's time spent in the the synchronization between the visualizations. It's time spent querying the DAX model. So a tool that we have in Power BI is a performance analyzer. And performance analyzer already does a number of things that are useful. So if I start the recording and I refresh the visuals in this page, you see that we have a measure that measure exactly the time spent to complete the rendering of each visual in the report. And the reason why I'm using this page is because I have many visuals here. And you see that you could sort this in a descending way, and you could see some information. But you notice that this is strange. I mean, there is something strange because we actually are not sorting by the duration of each visual, but by something else. So we have to, I want to explain one moment what are these numbers, because DAX Studio allows us to optimize only one part of these numbers. And we have to be aware whether we could do something with DAX Studio or we have something else to do. So let me explain what is going here. And let's start with the total time. The total time is how much time we waited between starting to refresh the page and having the data correctly displayed in the visual. A visual is a single item in the report, right? And when you click on a visual here, you see that, when you click on a visual here, you see that the visual that we are highlighting in the performance analyzer is also highlighted here. So you can locate the visual in the page. For example, the matrix here, which is the slowest one, is the visual that requires more time, is the only matrix we have in the report. Now, if you think about the time displayed here, it seems that we waited many seconds. The reality is that if you remember, we waited maybe 4 or 5 seconds before having all the visuals displayed. But if you consider each visual in the report, each visual waited maybe for 1 second or 2. But many of these operations were in parallel. So the reason why we have the total duration is how much time we spent waiting since the beginning of the refreshing of the page until the visual was available. But the reality is that every visual doesn't spend that amount of time. We don't have so many cores available to display everything in parallel. So what happens is that the operating system split the CPU between different operations, and also Power BI split the different tasks in different queues. And you see here 3 values, which are the DAX query, the visual display, and other. Now, the DAX query is the time spent waiting for the data from the DAX query, from the engine. And this is the part of the visualization we can optimize with DAX Studio. The visual display is the time spent to render the visual in the report. And you see that this time is milliseconds. This is just 47 milliseconds, which is a very small time, very small amount of time. We could have a very long amount of time here if we have a visualization with tens of thousands of points in a map, and then you could wait a few seconds just for the visualization, or you have a very complex visualization that is very slow. But otherwise, usually we expect this time to be very small. And finally, we have this other. Now, this other now is only 10% of the time, but if I go to some other visual, for example, this one, you notice that in this visual, other is 700 milliseconds, and the total is 724. So it seems that other is a lot of time, and people ask, how can I optimize this other? You don't have to, because this time is just time waited for something else. The visual waited for some other visual to be displayed. We have in this report maybe 50 visuals, and Power BI can only work on 1, 2, 3, 4 visuals at a time. The other had to wait, which means that other is time that you should ignore for the performance optimization. Now, this type of visualization is not ideal. I would have used a different way to display this data in this visualization. And the best thing to see this data would be in a Gantt chart, to be honest, where you see the starting point and the ending point of each visual. Now, however, the data that we have here can be exported. So if I click on this button, Export, I can save this data in a file. So let's call this this file here, performance Power BI performance data. You can change the name of the file, of course. So I save this file, and what I can do in DAX Studio, I can open. So let me go here. I can open DAX Studio, connect the Studio to my model here, connect, and you see that I have this button, Load Performance Data. And if I click this button, I can just load the same JSON file that I just saved from Power BI. This file has the same information that we have seen in that window, but we display this information in a different way here. You see that we have the name of the visual, and we have this important information when the query, the DAX query started and when the query ended. And for each row, we have the DAX query that has been executed. You see that it is much easier here to sort by query, by rendering time, or by total time. And total time is the sum of the query and the rendering time. So if we remove the other, this is a more realistic visualization of the total time spent for each visual. This is the column that I would have used in Power BI. But this is one type of analysis we can do. And this is one feature we have here, that is load performance data of Power BI. Now, the query you see here, however, is the same query that we could have copied from this copy query button. So the idea is that in order to render this matrix, Power BI generates a DAX query. The DAX query retrieves the data from the model, and then the result of this query, which is always a table, is used to render the visualization. Now, in this case, we have a pivot table, but we could have a chart, a line chart, a bar chart, or in this case, we have a simple card that is just a visual that displays the result of a measure. And in any case, every visual generates one DAX query. And so one first consideration is that this report will never be fast because it has to generate 50 queries instead of one. If we had a single visual with 50 cards, we would have generated a single query, and we would have removed the overhead of sending the query, waiting the result, and so on that exists for each visual. And so this is one of the problems of visualization, and the small multiples, which is a feature of Power BI that is expected later this year, should be able to solve part of this problem. There are already a few custom visuals that have some visualization like small multiples, and also car with states by OKViz will have this feature in a few weeks. Now, and this is a good thing for the optimization. But now I want to move to DAX Studio because the focus is DAX Studio. What can we do in DAX Studio to analyze the query? So first of all, we can try to copy the query here and paste the query here in DAX Studio. Now this query is the query generated to populate the. Sorry, this is the query for. Wait a minute. This is the query for the phone company. I'm not interested into this. I want to use this query here. Matrix, which is something that requires some time. So I pasted the query here. And when I have the query here, I can click on run and I can run the query. Now, if I run the query now, I will see that the result has the result of the query, which is the result of the execution sent to Power BI to render the visual. So you see that this is the same content we have here. With just one difference, you see that the total here is the first row here, but the total nature of this result is defined by this column, is grand total, row total. And every time you have multiple levels and subtotals, every subtotal defines a new column in the result of the query. This is the data consumed by the Power BI visual to create the visualization. But technically, what is happening is that we have to solve this query in DAX. Now, if I execute this query, I can see the result in DAX Studio, but how can I analyze the performance? We said that the PBI performance is just a visualization of the result extracted by the performance analyzer. I can, if you want, I can double click here and I can paste, let me do this. Like if I remove the data here, if I double click the same line that was the slowest one in the performance session, I paste the query here, and you see that you have some additional data. We have the information that were copied into the Power BI performance file. So this is something that you have only if you get the query from this export. The rest of the query is identical, and this is just a comment that helps me understanding when this query was executed. Now, I can format the query, of course, as usual. And what is interesting is using one of these other tools that we have here. We have in particular server timings and query plan, whereas all queries is another tool that can be useful to analyze what is going on an analysis services server or on a Power BI instance. Let's say that all queries is not so useful when you have Power BI and you use Performance Analyzer. But let's see what happens here. So we will, because it is a very similar feature to that of Performance Analyzer. If I start all queries, now DAX Studio is listening every DAX query generated by Power BI to the engine of the model, the analysis services engine that is running behind Power BI Desktop. So if now I click, for example, on this slicer, Europe, and I select Europe, what happens? All the visuals are refreshed. But every visual sent a new query. You see here, these are the new queries that have been executed after I changed the slicer. And if I go to DAX Studio, you see that here, all queries captured all the queries. You see that this is a slightly different table. We don't have, for example, the rendering time for the visual. We don't have other details. But at the same time, when you connect this to analysis services and there are other users connected to the same data model, you will see queries sent also by other users from other clients. for Power BI Desktop, you don't see much difference between this result and the load performance data. So this is not a feature we use so often with Power BI Desktop. We have a performance analyzer now. So let me go back to the single query. So let's say that there is something here. In order to obtain this result, which is just a few rows, 500 rows, I had to wait for 2 seconds. You see in output, you see the history of the executions I made in DAX Studio, and again the duration is always in milliseconds, and we waited for 2 seconds before getting the result of this query. Now there are 2 buttons here: query plan and server timings. Every time you click this button, you see that you see a waiting time, waiting for trace to start, just to wait to see this other message, query trace started. When you have Power BI Desktop, this is very quick. If you connect it to, for example, Azure Analysis Services, the time between waiting and the query trace started could be a few seconds, so just wait. Then I also can connect the server timings. This is another connection, another configuration of the trace. And you see that now we have 2 new panes here, query plan and server timings, that now are empty. Now, what is happening? DAX Studio is listening events generated by Analysis Services, which is the engine running the model. And these events describe what is going on in the engine. What is the query plan? What are the internal events? Let's start this. And please note that I'm using this mode, clear cache then run. I can also use this mode run, but if I use this button, which is the default usually, we execute the query without clearing the cache on the engine. Whereas I prefer to use this mode, clear cache and run, because I have more accurate information for the performance optimization. This is a simpler way rather than using clear cache, click here, and then click here. Instead of doing this every time, I prefer to do this. But be careful when you connect this to Analysis Services in production. You probably don't want to clear the cache every time you run a query, so pay attention. Because I usually use DAX Studio locally with Power BI Desktop, I want this option to be the default. And so I can set the run style here in the options so that I don't have to remember to change the setting every time. When I start DAX Studio, this is always my default, okay? Clear cache and run. So I click now once. Now there are 2 queries actually that are executed. The first one, clear the cache. The second one actually executed the query and retrieves the result. Now, at this point, we have to evaluate what is happening here. And the information provided here are information that describe what is happening overall for the entire query between the formula engine, FE, and the storage engine, SE. The engine of the engine of Analysis Services, which is the engine of Power BI, has 2 engines in reality. The formula engine is the engine that understands everything about DAX and also about MDX, by the way. And the storage engine is what understand how the data is stored, compressed in memory, but is an engine that is very quick, but has a very small number of operations and doesn't understand DAX. The storage engine is like a very, very simple tabular engine that has only simple operation like sum, subtraction, multiplication, division, and aggregation, filter, and join, something like that. Everything else, it requires the formula engine. And so the reason why you see that there is some execution in a formula engine, some execution in a storage engine, is because the query plan split the job between the 2 engines. Now, the query plan is what we have here. And you have these 2 lists, which are the logical query plan and the physical query plan. For those of you that know SQL, let's say that the physical query plan is the actual execution plan. There is no estimation here. We don't have an estimated query plan. We just have the what really happened. So the logical query plan is just a representation of the high-level operation that are requested by the query, but the physical query plan describes the operation executed to solve the query. and it corresponds to the actual execution plan of SQL Server. The numbers you see here are not estimated, but are actual values. You see that the query plan is just a list of operations, and sometime in records we have some number that describe what happened underneath. So this is a slow query. Okay, this is a slow query that is slow because I'm doing this operation many times. So before looking at this query, let me start with something simpler. So let's get another query that doesn't have any performance issue, like this one, AdventureWorks. So I go here, I paste the query here, I activated the server timings, I activated the query plan. Remember, I have to wait that the configuration starts, and then I start the query again. So the result now is just a number. This is the single number displayed in a card, but once again, I have a query plan here, which is this one. You see that the physical query plan still has a number of operations. It would be nice to have a graphical representation of this. Sorry, this is what we have. And the server timings is what happened in the formula engine, in the storage engine. So you see that this query ran very quickly in 3 milliseconds. So I didn't have any performance issue. And however, it could be interesting to see, okay, what happened here? Because this is a very simple query. So let's examine what we're doing in DAX. We have here 3 filters that define 3 filters applied by slicers and by other elements that we have as a filter in the report for that particular visual. So this visual has 3 filters active. If you see here, we have brand, AdventureWorks, color is black. These 2 filters are here, AdventureWorks and black. And Europe is the selection in this other slicer. Okay, so these are my 3 filters. These 3 filters have been passed as argument to summarize columns, and summarize columns just evaluates sales amount. Sales amount is a measure that we have here in this model. So if I search for sales amount here, you see the sales amount is a measure. Okay, so this query is doing what? Well, let's take a look at sales amount. Sales amount is defined here as a sum x of sales quantity multiplied by net price in the sales table. So we are basically iterating all the rows in sales visible in filter context, and for each row we multiply the quantity by the net price, sum the result. This is what we're asking. Now, I had to go to Power BI to do this, but the reality is that if I click here and I right-click and I click on Define Measure, I can paste the definition of the measure within my DAX query. And the nice thing of DAX Studio is that I can execute my query changing the expression of this measure, and this will have a local side effect only in this query. So I can override the measure defined in Power BI or in my model using the local one. So I copied the definition. Let's say that I multiply this by 100. Okay. Now, what we should see now is that when I run the query, this value should be 1 million. But unfortunately, Microsoft, in the last 2 versions of Power BI Desktop, introduced the regression, and this doesn't work. So now I will show you that the number is the same, but believe me, in the next release of Power BI Desktop, probably the one that will be out in a few days, or lost case scenario in May, they've already told me that they fixed this issue, and we should see the right number. So what you have to do now, if you want to simulate this locally, just rename this here and here and run the query again. And you see that now the number is the right one. If you see this video in June 2020 or later, you should have seen the right number in the first test too, because they're going to fix this problem. So this is very useful because I can try to change the definition of my measure and try to see if it fixes the performance issue that I have, for example, if I have a performance issue. But now my goal was to use, so let's go back to the original measure, because I want to explain you what are the numbers that we're seeing. And so let's try to execute this query again. Let's go in server timings and let's try to explain what is going on here. So if I go to the query plan, you see that the query plan has this operation at a certain point that says, okay, I want to get the result of a sum vertipack currency, sum vertipack operation. So basically what this operation is saying, I want to do an operation, I want to pass this operation to vertipack, and actually the result of the storage engine query is consumed here by this operation. And the number of rows returned by this operation is just one. If I look at the server timings, I see that, so basically what I'm saying is that this operation is saying, I want to use the vertipack engine to do the operation. And this, it would be nice if we had a way to double click here and go straight here, because the meaning of that row, we're executing one of the queries we have in this list. Which one? We don't know, because unfortunately there is no link between the query plan and the server timings connection. We don't have the information to establish this link. In this case, I'm pretty sure we have only one storage engine query, so it is this one for sure. And if you look at this query describes an operation in a syntax that is similar to SQL, which is called XM SQL. And this syntax is an internal representation that we can read, is a human readable representation of an internal binary format that describes the same concept. So we cannot write the queries this way, but this is a representation for we humans that can understand what is going on. And if you look at the query, it is doing what? It is doing the sum of an expression. The expression is this one. So if you ignore for a moment these cast and operation with different data types, we are multiplying the quantity by the net price. This is what we're doing. And for each row, we do this, and we sum the result of what? Of all the rows in the sales table, joined to product, joined to customer, where these conditions are true. And these conditions are exactly our, slicers, right? And these are the same conditions we applied using these three tags and these variables in summarized columns to the DAX formula. Now, those of you that are used to SQL will say, okay, this is much easier than DAX, I know. But again, this is just a way to make it simple, because this is internally different. And you cannot write any join. The joins are only available when there is a many-to-one relationship in the model. Okay, if you have many-to-many relationships or you have other kind of relationships, this cannot be a join. So you will always see left after join this way when you have many-to-one relationships, and the where condition shows the filters that you applied. Now we're lucky because everything we wrote can be described with a single storage engine query. We get the best performance when this happens. But if you remember, the other queries we had was very different. Because if I run this query now here, I have a lot of storage engine queries. You see that even though my result has 500 rows, I'm executing 1052 queries here. And the first query is this. The first query is saying, I want to get product name and quantity from sales joining product where the quantity is greater than 0. So basically what we are doing, we are getting a table that has two columns that has for each name, not for each name, that has name and quantity. For each row of sales, no. Every XM SQL query is always a select distinct query. So we only get the unique combinations of name and quantity from this table. And then what? And then we have a query that computes the distinct count of customer key, because this is the measure I'm computing here, customers. Let's take a look at what is customers here. Customers is, let me go here, is a measure that does a distinct count of a sales customer key, filtering sales where sales quantity is greater than 0. Now, I'm writing a bad filter here, and this is the reason why this query is low. But you see that the effect here is that every storage engine query computes the unique number of customers for one product, or actually for two products, for two combinations, product MP3 player E51 silver with quantity 1 and with quantity 2. So we just want to filter one product, and we want to get the unique values for one product, but the filter passed to this storage engine query has name quantity for two different combinations of name and quantity for the same product. Doesn't make sense. What is the difference with the next row? Just the filter. Filter. So guess what? For each product, there is a different storage engine query. Now, each storage engine query has a duration. The duration is how much time this storage engine query waited for the result. Where a CPU is how much time of CPU has been consumed. Now, the CPU time sometimes is bigger than the duration. Why? Because we might have multiple cores scanning data, and we could wait, I don't know, 20 milliseconds in duration, but we could have 160 milliseconds of CPU because we were using 8 cores. I will show you a bigger data model to show this. This model is too small. We cannot see this happens. But basically, this query would have run in 1 millisecond. The problem is that if we call 1,000 storage engine queries, we have to wait at least 1 second, and maybe something more, because there is an overhead for each call of the storage engine query. So what is happening here is that the query plan is not efficient, because you see here that we have the first execution that gets data from Vertipack, which is, I think, this one, the spool iterator here, is getting the DCN counter from Vertipack, and the first one here is getting the result of the product that we got at the beginning. And basically, what is doing this? What we're doing here, we are combining, we are executing a storage engine query for each product we got from the previous query. You see here, every query has a line here. So this is extremely inefficient. Now, in this particular case, problem is that I wrote a bad DAX query. I should have wrote this filter this way. If I execute the same query again, remember, if I do this now, nothing happens because I have a slow query running in 2 seconds because my change was not applied. So let me fix the measure straight in the model because of the bug. In theory, it should have worked, but as I said, the bug that we have now doesn't make this work. And so now I copied my fix here with the key filters. I click enter. Now I go back here. I can also remove this define here and execute the query again. Now, by using this new definition of the measure, the very same query producing the very same result ran in 7 milliseconds. Why it is so fast? Well, because the first query just gets the product name and the distinct count for each product. So the single storage engine query retrieves an estimated 1,050 rows. This number is an estimation. Sometimes it is not correct. And everything is made in a single query here, which is what we expect. We also have a second query, however. Why we have two? Think for a moment. The total here cannot be the sum of the products. It's a distinct count. So how many unique customers we have in the entire sales table, we have to run another query. So for each granularity of the matrix, we have different storage engine queries when you have a non-additive measure like a distinct count. And here, the same would happen for min, max, or something like that. And here we have the second query. So you see that also the query that ran the distinct count for 1,050 products run in 2 milliseconds. So the cost was only the number of iteration between former engine and storage engine. And yes, we still are paying 57% of the time in the former engine and 42% in the storage engine. But actually, look at the numbers, 4 milliseconds, 3 milliseconds. Remember also one thing. Any number below 16 milliseconds sometimes is just an estimation. It could be 0, 16, especially for the CPU time. You cannot measure very, very carefully this. So when the numbers are below 10 milliseconds, just ignore them. Also below 20 milliseconds. We don't start optimizing a query that runs in 15 milliseconds. We start when it runs in 100 to 100 milliseconds or more. So we have a simpler query plan. You see that we have a smaller number of rows in the query plan. We have a simple server timings. So the idea is that I have to understand how can I describe my query in DAX so that the query plan will be simpler, and most important, with a small number of storage engine queries, will execute most of the calculation. Now, let me spend some time describing in more detail what we have here. And in order to do that, now I want to use a bigger data model. This is a Contoso model. Let me show you the diagram view. So this is the Contoso model. Star schemas. Actually, this is a Snowflake schema. We have sales, product, store, promotion, customer, date, and so on. I have an empty screen here, but I have a few measures here. So let's say that I use, okay, I can create here a measure sales amount, which is equal to sum x of sales quantity multiplied by net price. I just create a simple measure to start my report. Once I have this, I can start crossing data by, for example, continent, and then let me just use a better visualization here. So I have something here by continent. I could put the continent here. I could put the, let's say, the product category here. And we already have this. Now, if you think for a moment, this query is fast. Look at this. How many rows we have in sales? We have 12 million rows. Okay, this database is 250 megabytes of data compressed in a PBX file. And every query runs very fast. Let me check this. So if I go in Performance Analyzer, I start the recording, refresh the visual, get the matrix here, copy query. So now I go back to my DAX Studio. I create a new connection, this time to Contoso. This is a different Power BI file. I paste the query and I run the query with server timings and query plan activated. So once I have this, I can show you that now the query was very fast, but I can start to see some number in server timings. Let me go here. Oops. Here we go. Now, you see that now we no longer see 1 or 2 milliseconds. We see something more, and we see different important information. So, for example, let's start from this. I'm thinking if I, give me 1 second, I want to create a snapshot because it could be simpler also for the video if I get a screenshot of this and I enlarge this here. So, okay. So in this way it's easier, and I can also use some highlighting here. So what we have here, this is the total time for executing the query. 16 milliseconds is very good. Okay, it's very good. But where we spent 16 milliseconds? We spent 16 milliseconds between formula engine and storage engine. Now the storage engine waited 11 milliseconds to execute the single storage engine query. The single storage engine query returned 66 rows. Now, if you remember, we didn't have 66 rows in Power BI. We have this in Power BI. But the reality is that the result you see here is a matrix. The result returned by the DAX query is slightly different. If we look at the result here is this. You see that you have 1 row for every cell of the matrix. And if you have line charts, you have 1 row for every point of the line chart. So the number of rows returned by a DAX query is the number of points or the number of cells you have. And if you create some conditional formatting using a measure, you are adding other measures that, however, are computed with the same granularity. So I expect to see additional columns, not additional rows. Okay, so the granularity of the query is the granularity of the visualization. the number of columns you see is the number of rows, sorry, is the number of measures that you applied to the visual, usually. Okay, this is just to give you an idea of what you should expect. This column index is telling on which column of the matrix this number should be displayed, basically. Okay, so this is what we get. So here, in several timings, we have 66 rows returned by the storage engine. This is the query in the storage engine. And let me check if this number is correct, 66. Well, if the number is correct, we should have 66 here somewhere, which we don't have. And if I go in the results, you see that we have 36. The number here is small, but it's 36. We have 36 rows. So it happens that the server timings provides a wrong estimation. Sometimes it's a bigger number, sometimes it's a smaller number. You never know. If you want the exact number, you have to look at the query plan, finding the operation in the formula engine that is calling that storage engine request. It's not easy to do that, but if you look at the columns, we have a category, continent, is ground row total, is ground. So if you look at this list and you look at the columns returned by this query, when you see a matching here, you know that you are looking at the right storage engine query. Okay. Now, so this is working well, but there is another information. There are other two informations here. The first one is this column, kilobyte, which correspond to this number. Now, if the storage engine query returns a list of rows, this list of rows has to be materialized in memory. And by the way, even though the storage engine works with compressed data, the data returned to the formula engine are uncompressed. And this requires a temporary table in memory, uncompressed. This is the size of this table in memory, uncompressed. Sometimes the query is low because this number is very big. If you see a big number here, you have several problems. The query is low, we are consuming memory. The query could go out of memory. The query could slow down the server if many users execute the same report at the same time. You have a performance issue, a scalability issue. So it's very important to try to keep this number small, right? Of course, if I create a query that returns 1 million rows in Excel and I want to see all of them, I have to return 1 million rows. There are no other ways. But most of the times in Power BI, you show a small number of rows. So we expect this query to return a small number of rows too. When you see that the storage engine is providing way more rows than the rows that you are displaying, it means that some filter or some aggregation will be done by the formula engine, which is lower than what the storage engine can do. So the kilobyte here is the size of the materialization in memory. And what is the CPU? Well, my machine has many cores. I don't remember, 12 cores, 16 cores. But for this particular query, because the entire table is 12 million rows, it has a maximum of 12 segments. So even with a big machine, I will never use more than 12 cores. Why? Because the storage engine can split the workload between different cores, allocating segments of the table to different cores. What is a segment? When you have a big table, more than 1 million rows, the table is internally split in segments. Each one has 1 million rows in Power BI. And this is the unit, the allocation unit for consuming the data. What I'm saying is that if you have a table that has 100,000 rows, you can have as many cores you want. You will always use only one core for your query because it's too small. The table is too small. But because this table has 12 million rows, I can show you that even though I waited only for 11 milliseconds, actually the query spent 109 milliseconds with the cores that we have. If I divide 109, so let me show you this here. If I divide this number, 109, okay, so this number here is divided by the 11 milliseconds here, is the ratio between the cost of the CPU, the waiting time. We have 9.9. This is the parallelism of the storage engine query. We were able to consume 10 cores during this query. If I only had one core in my machine, this query would have run 10 times slower. Okay, so you can understand whether you are using multiple cores or not, how much your storage engine query is scaling out using multiple cores. But when the remaining part of the query has to be solved by the formula engine is a single thread machine, and so you only use one core here. So this is another reason why we want to use the storage engine if we can. So in terms of how much time I wait, I sum formula engine and the storage engine, waiting time. But if I want to know what is the real cost of my query, I have to evaluate this number to understand whether could I have an improvement by adding cores to my machine? Will my query run faster if I had a faster CPU? This is the first number that you should look at if you have a query that is consuming time in the storage engine. When you find a query that consumes 100% of time in the formula engine and 1% in the storage engine, you don't have a problem in the storage engine. You don't have a problem that can be solved by putting more hardware. You just have to try to optimize the query, or if you have a faster CPU, you can go, 20, 30% faster. But you will never be able to go 10 times faster by just getting a faster CPU, because these days the difference between a slow CPU and a fast CPU could be twice. Okay, you can run twice faster. This is the maximum you can get for a server today. And but I have a machine with 100 cores. Doesn't matter, because if you're using the formula engine, you're using only one core at a time for one query. Of course, if you have 1,000 users, it's good, but for a single user cannot see any benefit. Now, these explain these numbers we see here and the relationship between these numbers and these numbers. So let me recap here. Let me remove this. So let's see if I can use another highlighter here, which is easier to use. Okay, so the number here is this. Then let's use another color. The number here is this. Now, we have a single storage engine query. If we had multiple storage engine queries, sorry, I used this one. Okay. If we had multiple storage engine queries, I wanted to use another color here, this one and this one. We would have seen the sum of this column here. So the number here is the sum of the duration. The number here, the yellow one, is the sum of the CPU, whereas the formula engine is only displayed here because we don't have a detail here for the storage engine. Okay. Now, another important information is the cache. If you remember, I said, okay, let's clear the cache every time I run the query. So you should not see this number unless within the same DAX query, the same storage engine query is executed multiple times. Sometimes it could happen, but not this time. Now, what happens if I change my execution using run query without clearing the cache? If I run this query again, this is what happens. You see that now I see the query here, but the query has been executed in 0 and 0. Why? Because it was in cache. You see the number here is 1. And another way to see this is the following. In this area of the server timing span, you can enable rows that normally are hidden here. But let me show them. Usually, we only show scan as an event type. But in reality, scan is the final event that is written here after an event of an event of internal or cache or batch. So we usually don't want to look at these internal events because we want to see only the result. But basically what is happening here, because I have the data in cache, this operation didn't scan the data in memory. It just retrieved the result of the previous operation. And the cache we have in Power BI in DAX is only at the storage engine level. So you can only improve the cache, a query that is low in the storage engine. If the query is low in the formula engine, sorry, formula engine doesn't have a cache. And only a few, let's say a few hundreds of the storage engine queries are stored in the cache. And so chances are that in the long run, you will not use the cache very much. The cache is useful when you continue to move around a report, and for some reason the same visuals are executed multiple times, and so the cache, reduce the workload. But if we want to optimize the DAX code, the best way to do this is to use this clear cache and run, so we always see internal instead of cache, which is the actual consumption. Sometimes a single scan event could have multiple internal events. Sometimes it is a 1-to-1 ratio. Yep.
Quick question around the caching thing. Actually, that's a really interesting point you bring up there. And I want to clarify something you said. The caching happens on, so if I'm in my local machine in the report in desktop, the caching is happening locally as I move between report pages. Is the same caching effect happening at the browser level when I'm looking at PowerBI.com, and the server side is also caching part of that data? So that way, if I again navigate between web pages of a Power BI report, the server is then still caching that information, but on the server side, correct?
Okay. No, it's a little bit more complex because the Power BI has its own cache system at the visualization level. So what happens is the following. Power BI, no matter desktop or web is this, or mobile, okay, is the same. So
Sure.
Power BI has a visualization layer that if you request the same combination of filters for the same visualization, it reuse the previous result.
Gotcha.
And it doesn't execute the query. And sometimes this is not what you want, because in the meantime, maybe the data is changed in the database, and you don't see the data updated. Sometimes it happens that you refresh the model and you see the previous data. You have to hit refresh, especially when you connect a report to an external data set. You have to click refresh to refresh the visualization. Sometimes it happens, right?
Gotcha.
So this is the cache at the report level, right? And it is not a cache at the DAX level. It is a cache at the report layer level. But once Power BI sends a DAX query to the engine, analysis services receives a DAX query, and here we talk about the cache of analysis services. Okay.
Gotcha.
So we only consider the queries that have been actually sent to the engine. When you run a report here and you don't see, you see DAX query, you see a dash. There was no DAX query, you cannot copy the query, there was no execution. Okay, only when you see the query, then when you see DAX query with a number and you see the button copy query, the query has been executed. Okay?
Makes sense.
Because this is important, because sometimes it happens that you change the rendering, but okay, these are
That's good. Thank you for the explanation. I was trying to clarify in my mind where the caching is happening, and that explains it really well. Thank you.
Yeah. Okay, so let's go back to DAX Studio, and I think we can just wrap up. And I think we explored more or less all the details of this. I'm thinking if I can show you something bad. So if I go here, let me write something bad here. So let's say that I create another measure here.
So we have a quick time check. We are we're about 7 minutes out. So feel free to take as long as you need. I don't want to rush you, but we have about 7 minutes left until the top of the hour.
I just show because I want to see if I can show you some number.
Yes, please.
It works bad. So I'm writing bad DAX code now.
Okay.
So
is that even possible? Can you even write bad DAX code?
Yeah. So this measures low big sales. If I replace this one here, you see that this takes a while. You see how much time it's taking.
Wow.
And it will be interesting to actually run the query in DAX Studio.
Do you have a zoom in on the formula? It's a little hard to see what formula you wrote in there.
Okay. Yeah. I can do this.
Yeah. Oh, perfect. That's better. Yep.
Okay. So this is the formula I wrote.
Okay.
Let me format this a little bit. So this is very bad DAX code. Don't write this. Never use some X filter. Don't do that. You have to use calculate. You have to use don't iterate, and don't call a measure in a big iterator. Bad. I'm doing very bad things here.
Excellent. Perfect. Thank you.
Okay, but you see that at the end I have some number here. By the way, the number could be also wrong, but this is not the point. The point is that if I copy this query, that runs in 30 seconds, copy the query here, and I go in DAX Studio here, Now I go here, I paste this query, I clear cache and run, and here we go. Now I run the query, and you will see at the end that the reason why this query was so slow is because I'm waiting a lot of time in the storage engine. But why? Because the storage engine is creating a large materialization, a large number of rows, is consuming a lot of memory, and this is the reason why it is so slow. Now, the formula engine will be slow too, because once the storage engine created this big table, the formula engine has to consume this table. So let me copy this data here.
Holy cow, there's a whole lot more stuff down there.
Yeah. Wait a minute, I made a mistake. I had to enlarge this because otherwise you don't see that these are 12 million rows. So let me get this again. And copy, and here we go. So you see that what we have here is the following. We have the total amount of time we waited was 23 seconds. And we waited 10 seconds for the storage engine and 12 seconds for the formula engine. But you will say, okay, we have a problem in the formula engine. No, we have a problem in the storage engine. This is creating a too big materialization. We are creating a copy of 12 million rows uncompressed in memory. And we send these rows to the formula engine that has to do the calculation in the formula engine. So we are basically getting 200 kilobytes of compressed data, expanding them in 5 or 6 gigabytes of RAM, and then the formula engine has scanned this uncompressed data to do the calculation. So this is just a way to show you that it's clear that sometimes you have to be able to interpret the data. And for this reason, we show these numbers. Don't look just at the number of the CPU. Look at the why it is taking so much time. So if I have a long number, a big number here, I look, I could sort by CPU in a descending way. I look at the rows. I look at the kilobyte, 1 gigabyte estimated size of this materialization. So it is visible that we have a problem. And even though we use the cache at a certain point, imagine that this query was in cache, we would still spend 12 seconds in the formula engine. So the cache here will save only this 10 seconds. But the problem is the formula is written so bad that is doing an operation that is totally useless. And so, this is just an example to show you that the understanding how to interpret these numbers takes several hours, if not days, of course. And so I can show you that if you want more, more details about this, how to work with the optimization, we have several chapters in this book that are just dedicated describing query plans, storage engine queries, and so on. And we also have this training, Optimizing DAX, which is just about optimizing. So you have to know DAX, and then we have to, you can spend a few hours trying to understand how to work with these numbers, how to understand where is the DAX part that you have to optimize. But DAX Studio is the first tool you have to use to retrieve these numbers. Otherwise, getting these numbers without DAX Studio would be pretty much impossible, because these are events you could capture with Profiler, but it's very, very, very time consuming.
And you said so I threw a link in for your book. I already grabbed the link for the book.
Yep.
And then I want to grab the link for your training class. Which training class is it? Because I want to make sure I grab that and be able to share that.
Optimizing DAX video course.
Optimizing DAX. Oh, got it. Optimizing DAX workshop. Is that the one we're looking for?
Yeah. Optimizing. Yes.
Okay. I'm going to just make sure I grab that link in there and put it in there as well, because this is gold. This is so much good stuff. This is absolutely amazing. And my mind is blown by how this is peeling back those walls. I mean, again, I'm a business user and I'm coming in very much from the front side of things. I'm really just building Power BI and kind of seeing what kind of shakes out. I'm not really understanding all the details of the engine itself. So this is super huge for me to get really down into the details here and really start performance tuning on larger data sets. And I think that's where you're going to see most of your performance hits. When you get to these large size, you really do have to know what you're doing.
Yeah. Yes, you can investigate a lot, and sometimes the analysis is not. We use a very, very simple measure. As soon as you have more complex DAX formulas, you see that the query plan could go up to thousands of rows, and it's very hard to understand.
Yeah. Makes sense. This is a great example.
Any questions?
No, we don't. Actually, hold on. We do have one more. So we have
Good
one
morning.
more question. Yeah.
Yeah.
So Prabhav says, this is super helpful. He goes, when can we get the recording on YouTube? So this is awesome. We will get the recording out there as soon as we can. It's going to be about 1 to 2 days. I'm trying to crank them out. I have the video done for the intro class, or the introduction with Darren. That will be done hopefully out today. And then I'm going to start trickling all the other videos out as I can get some more time to edit them. And that's it for questions. I'm flabbergasted. I just love watching you present. It's so good.
Okay, good. So
with that, I will just quickly share my screen here. Let me get the final screen up here, and we'll do that. Hopefully that publishes. I hate that Teams takes away my screen every time I do this. There we go. I think that should. There. Thank you everyone for attending the webinar. Marco, your wealth of knowledge is absolutely incredible. I'm so excited that you're able to do this with us. Please, let's do this again in the future and do some more fun little tutorials here and there. I think this is awesome. Thank you for your time. I appreciate it. Stay safe and have a great weekend.
Thank you. Have a nice weekend. Bye-bye.
Thank you. Bye-bye.
Thank you. Bye-bye.